a real-time situation.
Okay,
What is
no,
there?
so what you need to do, Rajesh, is you send me the data. You send me the
Okay.
data. I may not be able to immediately tell you. I may take some time to analyze the
Okay.
data, and then based on that, we can build some models around it. Okay.
Okay.
So
Okay.
what broadly, what kind of features you have in your data?
So it's actually a cycle time calculation sheet,
Okay.
and based on the cycle time, there's an incentive which is paid to the associates.
Okay. Okay.
So here the main challenge what is there is to predict the efficiency through this cycle time.
Mm.
What may be the efficiency improvement required in certain stations. There are different stations and different assembly lines
Mm-hmm. Mm-hmm.
where these cycle times are captured. There are
Mm-hmm.
some allowances also given to the
Mm-hmm.
associates,
Mm-hmm.
some setup time allowance and things like that. So
Mm-hmm.
based on that, some calculations are made, and based on the efficiency, the incentives are paid to them.
Yeah, but make sure whatever I could understand from your data, I may be wrong. I need to understand the data more. But what my primary feedback is that this is not a machine learning problem. Okay, it is a physics-based problem. So understand that, or engineering-based problem. Understand the difference between the two. In fact, a few days back, I was talking to another client from a chemical industry, and they had a very similar kind of situation. Many times you confuse between a physics or based or engineering based problem and a machine learning problem. So if I have to
Hmm.
calculate cycle time based on certain formula, certain engineering formula, and based on that formula, again, I have another formula to calculate the incentive. That will not be a machine learning problem. That will be an engineering problem, because you have to use certain engineering principles to calculate the cycle time, okay, or the inefficiency of the cycle time. It will
Hmm.
become a machine learning problem only when the output is based on some data. For example, not on formula. Okay, for example, I'll show you a dummy data set, and we'll work on that dummy data set today. Uh, there may be some dummy data about different machine parameters like vibration, temperature, etc. Okay, and along with that, you have data whether a machine at that point of time when the vibration temperature data was collected, whether the machine failed or not. Or for example, what is the mean time between failure? Now that is a machine learning problem because it's not based on the formula. It is based on certain parameters are given. Against that parameter, there is already a past data that the machine has failed or not failed, or what is the mean time between failure. And then based on this, I am using a machine learning model to predict the mean time between failure or predict whether the machine is going to fail or not using any engineering formula. Okay, this is very, very important. Your use case should not be a case where engineering formulas are used. Okay, because there is an engineering problem, is not a data science problem. Okay,
Right.
but still you share the data with me, but prima
I'll share.
facie,
Yeah.
yeah, it appears to me that this is a more of a I am going to share an artificial data with you. See if you have, you should be having, being in manufacturing, you should be having similar kind of data. Okay, so see if you are having this kind of data. I'll first share the data with you. This is an artificial generated. In fact, I have generated this data through ChatGPT. Okay, so these days, good thing is that you can use ChatGPT to generate data. Okay. But then, I mean, of course, you have to give prompt that what kind of data you need, what are the input parameters you need, etc., etc., and it gives you a very decent data set. But obviously, these are artificial data sets. It can at best act to help explain the concept, but it will not give you the experience of working on real data, because when you work on real data, there are various other problems that are going to come in. Okay, and some of the problems we'll talk about it, but unless you work on real data, and this being a work integrated learning, that's I think the spirit of work integrated learning. Unless you work on your real data, your learning never is going to be complete. Okay? Otherwise, learning will be very, very theoretical. It will be like any other MBA course. Okay, so you have to get the data from your organization, and this doesn't apply only for this subject, applies for every subject. Okay, you have to get data from your organization. So I'm just sharing this file with you. I've shared the file with you. I'll share the screen also so that everybody can you download that file. So, are you able to see the data set? Yes.
We are able to download, but from your screen, we are not able to see.
You should be able to see it showing me sharing.
Now it is, yeah.
Oh, okay, okay. It took some time. Okay, I switched it off. Just hold on. Yeah, I think it took a little time. Okay, so you see that essentially what it's a completely fictitious data which I made up. I made up my mind, no, from my mind. You try to get because you also manufacture. Do you manufacture medical equipments? I think yes, right? Yes, no. I know washing machine is one of them. It can be also washing machine. But other so this one I basically I assume that there is a CT scanner, and this CT scanner we are trying to predict the mean time between failure. Okay. The mean time between two failures for different types of CT scanners. Okay, and these are the different CT scanner, the IDs. Then I have certain data like age of the machine. Okay, how old is the machine? This is last service. What is the ambient temperature? Let's say this was an ambient temperature, average ambient temperature when the machine is running, machine temperature, vibration, radiation, voltage fluctuation, pressure bar, if the machine is giving some error code, usage mode, okay, high load, location, like this. Okay, so these are some of the factors that or features I have provided. So remember, any machine learning problem, it is shown that the features that will affect the outcome is more or less known. Understand this statement very carefully. The features that affect the outcome is more or less known, but how they affect the outcome is not known. For example, when you're saying cycle time, if I am able to define an exact formula for cycle time, that will not be a machine learning problem. That will be an engineering problem. Because I know that what are the factors that affect the cycle time, and I also know the formula. So there is no question of any prediction there. It is deterministic. But suppose I know the factors, but I don't know, I know it affects the output. Okay, it affects the cycle time, but I don't know the formula. I don't know the formula, how it affects. Okay, maybe there are many other factors which I'm not able to identify. Maybe because the formula itself is too complex, so nobody has been able to really find out what the formula is. But people know that there is some relationship between, let's say, ambient temperature and mean time between failure. But nobody has really been able to find out a formula that states that if this is the ambient temperature, this will be the mean time between failure. Okay, so this is a criteria of any machine learning problem. Otherwise, it doesn't qualify to be a machine learning problem. There's a big issue, as I was mentioning in one of the other clients, that somebody else was trying to some other consulting company was trying to sell machine learning as a solution to their problem, but actually their problem was never a machine learning problem. It was just a engineering problem. Okay, and that they knew very well because they are the experts in that industry. Nobody else can teach them how to make it better. Okay, so these kind of disconnects happen. And these are the things that you must investigate in your organization, because that's where your real value for the education comes. Otherwise, it's all theoretical, and it's like a fresher, what a MBA fresher does. Okay, you are different from that. Okay, anyway, so this is fine, and this is a mean time between failure. Is it okay? Okay, all good?
Yes.
Okay. Now, one of the few things you should notice in this data set, first of all, tell me what are the features and what are the what is the target or outcome? Which is the feature and what are the features and what are the target and outcome? which is what are the features of this data set, and which is the outcome or the target of this data set.
Features is ambient temperature.
All of these are
Location.
features. Yeah. Yes. And outcome is mean time between failure.
Mean time between failure.
Okay. Is it a regression problem or a classification problem? We have not done classification yet, but we know broadly what it is. In classification, we know that it is, positive or negative. A patient is diabetic or non-diabetic. Customer will churn or not churn, like that. And in regression, it is like what is the expected sales, predicted sales based on the ad spend. So this problem is a classification problem or a regression problem?
Regression problem.
Regression problem, because we are trying to predict what is the mean time between failure. If we are trying to predict, we'll share another data set where we are trying to predict whether a machine is going to fail or not. That will become a classification problem, but this is a regression problem. Okay. Okay. So as far as the features are concerned, you can see that there are two types of, there are few categories of features. First category of feature or first way of categorizing the feature is that there are some features which are categorical values and some features which are numeric values. For example, let's say usage mode is a categorical value, location type is a categorical value, and there are others which are numeric. Days since last service, ambient temperature, etc. These are all numeric. How is the treatment of these two features different when we try to build a model? How will the treatment be different if we try to build a model? How will I treat the categorical value? How do I, or do I need to treat them different for a regression?
Yes, we have to treat them differently.
Okay. Why we have to treat them differently?
Because this categorical value needs to be, I would say, converted into a numerical value.
Okay, but why do you need to do that? Do you need to do that in all kind of machine learning problems?
Need not be.
Need not be. Okay. We need to do that in regression because regression is an equation. In regression, we try to derive a mathematical equation. Unlike, let's say, something that decision tree, which is not an equation, which is a logical tree, if else. If it's a logical tree, it doesn't matter whether a value or a predictor is a numeric value or a categorical value, because I can always say if the location type is urban, this is what will happen. If the location type is rural, this is what is going to happen. Is not an equation. But when you have a regression problem, it is an equation. So I cannot have, y equal to mx plus c, okay, where x, the value of x has to be a numeric value. It cannot be a categorical value. So one thing is that I have to, because there are some categorical values and I am solving a regression problem, I have to convert the categorical value to a numeric value. Otherwise, regression will not, we will not be able to use a regression form. And how do I convert that? How do I convert, let's say, location type, urban, rural to numeric?
By assigning them to maybe 1, 2, 3.
Okay, okay, so we assign urban 1, rural 2, semi-urban 3, like that?
Yeah.
Okay. We can't do that, because if we do that, what is going to happen is y equal to mx plus c. So if the value of x is higher for certain cases, okay, a category is a location type is a categorical value, and there is no, it is what is called a cardinal categorical value, not ordinal. There is no order. There's nothing which suggests, let's say, urban. If it is an urban at least not as of now, that if the CT scanner is located in an urban location, the mean time between failure will be higher. And if the location is rural, the mean time between failure will be lower. There is no, as of now, there is no evidence of that. Okay. Eventually there might be some. Okay. But as of now, there is no evidence. So I cannot have a categorical value represented by an ordinal value. 1, 2, 3 is ordinal. There's an order. So moment I say rural is 3, rural will carry a higher weightage, y equal to mx plus c. If x is equal to 3, y will have a higher value, all other things being equal, than if x is equal to 1. Because by the nature of the values. Okay. So whenever you have categorical values, you cannot have directly replace the categorical values into numeric values. Okay. So what do we do? How do we replace the categorical
frequency
value?
encoding?
Yeah.
We can frequency encoding. Frequency encoding.
Frequency encoding. Meaning?
Meaning the more urban we call it, give 1, rural 2 if based on the
no, that's the same thing that we discussed. No, that's the same thing. Then I'm going to give a certain value to urban, 1 ordinal value to urban, which kind of will influence the outcome. Okay. By default, I'm making the outcome influenced by rural more than urban. We do it by something called one-hot encoding. What is one-hot encoding? One-hot encoding is, instead of location type, I change this column. I don't use this location type column at all. What I do is I call a column urban. I create a column called urban. I create a column called rural. Are you able to see? I create a column called semi-urban. And then if it's urban, I write 1 here, 0 in other 2. If it's rural, I put 0 here and 1 in rural. So I have 3 features actually: urban, yes, no; rural, yes, no; semi-urban, yes. And I have a value 1 if that particular characteristic is valid. This is called one-hot encoding. Why one-hot encoding? Because out of these 3 values, only one of them can be 1. 1 is a hot because 1 is assuming that the electricity is passing. So 1 is hot and 0 is cold, no electricity passing. So it's called one-hot encoding. So whenever you have categorical values and you're using a regression model, you have to convert the categorical values into numeric by using one-hot encoding. Clear? As of now, I'll just remove this. Any question, yes or no? Yes? All good? Okay. Is there any feature? Is there any feature which should not be used? Is there any other features apart from all the other columns? So we are assuming that apart from this column, MTBF hours, everything else is a feature, right? Everything else the feature, okay, which are used to predict. Is there any feature that should not be used?
ID, machine ID?
Machine ID. Why it should not be used?
It's look ordinal and it can
Sorry?
give some ordinal. It looks at 1, 2, 3, 4 and it can influence or it can assign some value to it.
No, I did not get that. What is that?
it can also be treated as some number and then give some significance because it's not.
So it can be treated as some number, right? If I want. Okay.
Yeah.
So why? So if you are saying that this is because it is a categorical value, we have already seen that categorical value can be replaced by ordinal numeric values. So that cannot be the reason. Okay. If machine ID is required as a feature, then we can always convert that into numeric value. But if you're saying machine ID is not required, and not only not required, if you put it, if you keep it, actually, we may end up having a wrong model. Why would we say that? In other words, we are saying that we should not have machine ID as one of the features. There are two things. One is it's not required. That is one thing. The other thing, if we have it, it will actually deteriorate the model. First of all, which one is correct? And now why is it so?
So machine ID should be kept as a unique identifier so that the pre and post condition can be compared.
No, pre and post condition, there's nothing pre and post condition. We are just trying to predict this, okay? And there is a set of data. Oh, what you are saying that for which machine? Yes, that is okay. That is just so that's a key. That's a primary key, you can say. Okay, but that is not a predictor. That's not a feature. So you are saying that it can be kept as a primary key of a row, but it should not be used as a predictor or a feature. My question is, why not as a predictor or feature? Yes, of course, it's a primary key, and we understand it's a primary key is required for the table. But why it should not be a feature?
The significance is very less.
Okay. Okay. So the technical answer to this is these are high cardinality value. High cardinality value means and this is applicable only for categorical values, not for numeric values. High cardinality value means there are a lot of possible values, a large number of possible values. So if I have 1,000 records, I have 1,000 different machine IDs. What happens if I have 1,000 different machine IDs? There is no pattern I can identify because each record is a different ID. So unlike other cases for the other categorical values where there is a possibility of identifying a pattern, let's say for location type, there are only 3 possible values: urban, rural, and semi-urban. So there is a possibility of identifying a pattern of location type or relation of location type with mean time between failure aborts. There's a possibility of having a pattern. But if you have a large number of different values for each of these individual rows, it is not possible to identify any pattern. Okay, because each value is giving an independent output. So this type of values or this type of features are called high cardinality features. The cardinality is very high. Okay, those of you who have done entity relationship diagram, this means it's 1 is to n, n is to 1, m is to n, like that. Okay, so this is called cardinality. So 1 is to n, where n is a very high number, it's a high cardinality value. Any value that is high cardinality, this is not just unique identifier. Let's say in the location type, there are, let's say, 500 different values. Suppose the location type was indicating cities, names of cities, and there are 500 different names of cities. Same thing would have applied for location type as well. The location type would have been a very high cardinality value, and if we build that feature, the model will get confused because model will we are telling the model there is a relationship between location type and MTBF hours. And model is trying to find a relationship, but actually it is very hard to find a relationship because there are so many unique values. So any high cardinality value while building the model must be filtered out or removed. Is this clear, everybody? Yes, no?
Yes.
Great. Okay. Now the third thing before we finally go ahead is you see that these data types are not data types exactly, but the source of the data is different. For example, when you are getting the data like ambient temperature, machine, these are coming from sensors. And these are streaming data. Whereas age of the machine in years or days in your last service is probably coming from your ERP system. You are also having some ERP system, probably SAP. Okay, so there'll be certain data about the machines that will be there in your ERP system. And there are certain data that is coming from your sensors. How do you combine these two data? That's a very big challenge. So there's a whole concept of data lake and how Industry 4.0 works. Okay, so all of those things. So later on, if time permits, we'll try and see how all of these things can be used in a data lake. Okay, I'm not sure. Are you aware if you are using, let's say, an AWS or Azure? What platform? What cloud platform are you using? I'm sure you're using one of these cloud platforms. Okay, maybe multiple for this kind of data. Okay, either AWS or Azure or Google Cloud Platform. These are the three leading. Is anybody aware of which one is Bosch using? Yes, no?
I'm not sure, but I think we are using Azure.
Azure, great. Okay, if you are using Azure, then what we can also do is, do you have access? Do you guys have access to all these data lakes and all?
No.
The data for this data. So who in your organization have access to this data? Because you are business users, I assume. So you should be having access to some of this data. But then if you're using Azure, who has access to this data?
We have a digital team.
Okay.
Separate i4.0 team. They are the administrators of this data.
Okay. But then how do they interact with the business? For example, let's say you as a business have a problem. Okay, for example, you want to predict, as I said, that the mean time between failure. How do you work with the digital team?
So any projects, the user or the domain users will give the inputs to them, and based on which they will handle the data, and then they will give the solution.
Okay, but you are not working as one team to work together and find out the solution. I mean, you are just
inputs
yeah.
No, it will be together only. But most probably they will handle all the tools and systems, the inputs and the solution part, how it is required, and things like that will be involved from the user side.
Okay. Because anyway, I'm not very clear about the governance, but let's say you have to test a model or something like that. I'm not sure how to do that. Okay, because as a user, if you have to test a model, that whether the model is accurate or not, or is it the digital team only is testing that and giving it back?
They will only do, yes.
Okay. Anyway, so that's because those are very important things, because otherwise, I mean, if the objective of this course is to come up to speed with analytics, then I think it's very important for you to work with the digital team. Okay, because otherwise, you will not be able to apply your knowledge. Because if the digital team is doing everything, then where do you apply your knowledge? Right? Yeah. So that's something that you need to sort it out, because otherwise you'll not be able to apply your knowledge, because you have to work with that team. Anyway, so let's go back. What we were talking about is so these are high cognitive values. So these sorry, where it all started. So you have for example, Azure has a data lake. So the purpose of data lake is to be a repository of all sorts of data. Okay, for example, if you see that the ERP system has data about age of machine and days since last service, whereas the sensor data is coming from here, right? So, and if I have to use both the data to predict my mean time between failure, I do not have one place where I get both the data, right? Because my my data about this age of machine and days since last service, that is available in ERP system, whereas the sensor data, everything is available in my let's say it is coming through a streaming data. Okay. So usually what happens is data lake is one repository where all sorts of data is first dumped. So you don't have to define the schema of the data beforehand. You first dump the data and then you figure out which data is to be used, okay, how it is to be used. You define the schema and then you use it. Okay. So this data typically comes from the data lake. Okay, like what your digital team, they must be using a data lake to get this data. Okay, and then they will be building the models. Okay. So let's see, then we use this data set and we will build a regression model. Okay. Predicting okay, so everybody is able to see my screen? Yes. Okay. So what is the first step that we should do? Everybody should, when we have done this with another data set, so should not be a big problem.
You have to read the data.
Read the data. And I think the file that I've sent to you is an Excel file. So we can use the Excel reader. Okay. So just read the file. So you have to remember these basic steps. Okay, these are the important thing as far as your exam is concerned. This is important. Okay, so give me a warning. Let me check. Okay. Okay, so we have got some data, some statistics also. It is artificially generated data, so there will be no missing values. But in reality, you might have some missing values, and in that case, you may have to treat the missing values. And remember, the first thing, the basic, or rather the first port of call in treating missing values is always removing the rows that have missing values. Okay, even though there are more sophisticated techniques, but this is the basic, the first port of call. Only if you are not able to remove the rows, then only you try to replace it with representative values. Okay. What is the next step that we want to do?
Filter whichever data
Very
is
right.
not relevant.
Filter the in this particular case, yes, there can be other irrelevant data. but we'll see what other irrelevant data is. But in this case, the first thing that comes to our mind is the high cardinality values and the machine IDs. Now you see, notice here that whenever you import the data set, it always creates a primary key. Okay, a new primary key. Now everybody, I hope, knows what is a primary key. Primary key is that attribute of a relational database management system that uniquely identifies a row. Okay. Now you may ask that why it did not take machine ID as a primary key, because the system doesn't know or doesn't want to take any risk whether the machine ID is actually unique or not. Okay. We don't know, because this data has been generated from some other place, and this data is not necessarily coming from relational database management system. So there is no guarantee that the machine ID is unique. So that is why in such cases, you will see that whenever you're reading the data, even in Python, when you're reading it and creating a data frame, it will always create a new primary key, which it knows that it is unique. For example, in this particular case, it means KNIME knows, or Python knows that this is unique. In this case, it is a row ID. So a new ID of row ID has been created. Okay. Now, so we need to do that, and we will use a column filter for that. So we will take away machine ID. Things are fine. Execute that. Okay, great. What are the next steps that we want to do?
We should have training and testing data separately.
Okay. Yeah, but before that, we have a lot of things to do. Okay. So usually what happens is, when you have this data, the first thing that you do is something called exploratory data analysis, EDA. Why do you do exploratory analysis? In order to figure out if there are any actions to be taken on the data itself. You may say, what kind of action? A very simple example is that let's say if there are any outliers, if there are certain values which are outliers, then obviously if we have that in our data set, then it's likely to, in most cases, not in all cases, we'll come to where outliers cannot be removed, in fact. But in many cases where, there are outliers, it probably, if we use that as a part of our learning and ask the model to learn from that, it will probably lead to incorrect results. So probably those outliers may need to be removed. But there are cases where you cannot remove the outlier, where the cases of, let's say, the certain class, okay, not so much applicable for regression, but certain classification problems, where a certain class of that problem is occurring very rarely. For example, fraud detection. Okay, when you have, let's say, fraud, banking fraud, out of millions of transactions, or probably billions of transactions, one transaction is likely to be fraud. So if I get the data and kind of do an analysis, I will always see the fraudulent data to be an outlier, because it is the fraudulent data which will show some anomalies which is not available in normal transaction. For example, let's say the transaction might be happening from a very a location where typically that particular credit card is never transacted, is happening for a value which is never transacted. So there will always be some anomalies. Okay, and such case will be very, very rare. So if I remove a fraudulent transaction, or a anomaly rather, outlier, from a data set, I will be possibly removing most of the fraudulent transaction and my machine will never be able to learn. So in such cases, I cannot remove the outliers. Okay. I have to do something about it. Okay. Should I keep the outliers or what? That's a different question. Okay. But as of now, that those kind of cases will not be able to remove the outliers. Okay. But other cases, many other cases, we might have to remove the outliers because otherwise my machine will learn from wrong sample of data. So that is one important thing that we need to do. Another important thing that we need to do, or many times is done, is called the correlation matrix. Correlation matrix means that what is the correlation between two variables, let's say ambient temperature and machine temperature, ambient temperature and machine temperature. Are they correlated to each other? That means if the machine temperature is high, the ambient temperature is also high. You may say, what is the relationship? Why is it so important for us? If two parameters are highly correlated with each other, and if both of them are present as predictors, suppose these two parameters, ambient temperature and machine temperature, they are highly correlated and all other factors are not correlated at all with each other. All other factors are independent of each other, whereas these two features are highly correlated, then these two features will dominate the outcome over others. It is like two features, y equal to m1x1 plus m2x2 plus m3x3 till mnxn plus c. So if x1 and x2 are highly correlated with each other, then what is going to happen? When x1 increases, x2 is also increasing. Whereas that is not the case for x3, x4, x5. They are varying randomly. So x1 and x2 will dominate the outcome compared to all other features. Clear? Yes or no?
Yes.
Right. So now in this case, what should you do if they are highly correlated to each other? Now this is where the reason why I'm asking what is your interface with your digital team. Okay, that is how is your governance where your business team is working with digital team. That is very important from a governance and from an organization process perspective, is because who defines these features and who defines or who figures out whether there's a correlation or not. Features have to be defined by business people like you. Because what did we say? We said that the case for machine learning is where I know the outcome is dependent on the feature, but I don't know how the outcome is dependent. I can't define a formula. If I can define a formula, it's an engineering problem. It's not a machine learning problem. I'm not able to define the formula, but I know that the mean time between failure depends on ambient temperature, machine vibration, blah, blah, blah. Who has to give that input? Not the digital team, because digital team they're not the business guys from engineering, core engineering, or let's say from sales. Who will vouch for these are the features on which the outcome is likely to affect? And then
domain expert.
Domain expert, absolutely right. Because once the domain expert tells this, then the digital team has to come back and say which of the data they can capture and how are they able to capture it. They may come back and say, look, we can't capture vibration. Our sensor system is such that as of now, we can't capture vibration. Right? So the business team has to then say, oh, if you can't capture vibration, there's no point in doing the prediction, because vibration is such an important parameter. Without vibration, there is no point in doing a prediction. Or the design, the domain team can say that, okay, fine, if you're not able to capture vibration, there is a surrogate measure. Let's say whatever, noise. Can you capture noise? Because noise, if the noise is high, the vibration is likely to be high. Now, who will give this input to the digital team? Digital team can't decide this. And so that's why this handover is very important. Handover means to and fro. So anyway, so once that happens, when there's a high correlation, then the business team has to say that, should I drop one of them? because they're highly correlated. Okay, I don't need the ambient. I just go with the machine temperature because that's good enough. So those are highly correlated. I can take only one of them. Or they may say that no, I am going to create an artificial metric, which is a combination of ambient and machine, ambient temperature and machine temperature. It's like saying that I have height and weight, and I have an artificial metric, height multiplied by weight. Or let's say ambient temperature multiplied by machine temperature. I create an artificial metric combining both this metric. Okay. But I have only one metric. So this kind of thing is called, I mean, there are many methods. One method is called principal component analysis, PCA. Okay. So it's important to know how are these features interrelated with each other. And you do that by finding out what is called a correlation matrix. Correlation matrix is like a n by n matrix, where each feature is correlated to another feature. Is correlation with itself is always 1, and correlation with other feature will be either the maximum value can be +1, the minimum value can be -1. +1 is highly correlated, -1 is also highly correlated, but correlated in the opposite way. So these are some of the analyses that you have to do before you can actually, decide that how many features you are going to take and which observations you are going to take to build your model. Okay. So is everybody clear? Yes or no?
Yes.
Okay, great. And one thing also is very important, because all of you are business users, is import. So tools like KNIME, and today, if you look at Colab notebooks with Gemini, they have been built to assist business users like you. So you as business users should bring your project to a state where you have a prototype ready without any dependence on IT or without any dependence on digital team. That I should be independently able to put a project ready, a prototype ready, and only when I need to scale it up, deploy it, I go to the digital team and ask for deployment. Till that, I should be able to do it myself, because then my agility to experiment increases. Otherwise, what will happen? Every time I have to go to the digital team. I want to do this, and digital team will say that I have other priorities. So you will not be agile. So that's the, I mean, in a modern, we are calling it democratization of IT. So in modern organization, IT has to reside in every department. IT cannot be in only one department. Okay. The core IT will be in one department, but all other digital functions has to be democratized. It is distributed across multiple departments. So these are fundamental strategic changes that has to come in organizations to enable this kind of transformation. So we will do this, and so let's see. The first thing that we are trying to do is outliers. So how do which kind of charts do we make for outlier identification of outliers?
Box plot.
Box plot, right? So we can make box plot for all of them, but let's do only for one, so that let's say machine temperature, we'll do a box plot for that. Okay, so you have this, see, few outliers are there. Okay. Ideally, I should remove these outliers, but for now, I'm just leaving it like this. Ideally, I should remove it. That's the whole purpose. Okay, but then the process will get longer, so I'm not removing it. Okay, and these are the nuances where obviously you need a little bit of coding knowledge. It helps. You can do it on KNIME also, but then in KNIME it becomes a little complicated in building the workflow. So a little bit of coding knowledge helps. So, but What is important is that I should be able to build a prototype. So even if I'm not able to remove the outliers, it's okay, because my objective is not to deploy the model now, but to see if a prototype works. Okay. The next one is correlation. So use a linear correlation.
Sir, in the box plot, we directly have to execute, or we have to select some specific fields?
No, I selected only specific field, because otherwise it will because you have to create a box
Machine
plot for
temperature.
certain features. So I selected machine temperature and create a box plot for that. Okay, so we are doing a correlation. So remember, correlation can be done only for numeric data. So all the categorical values should be filtered out. So should be for the outcome, MTBF, because we don't want to find out the correlation with MTBF, because that's what the final model is. Our objective is to find out the correlation between features so that no feature is getting extra dominance. Okay, so that's what we want to do. Okay, so we'll do this and we'll run this correlation. And you see, okay, so first you see, first you see this correlation matrix. Is everybody understanding what this matrix is about?
Professor, could you explain that linear correlation once again?
Linear correlation. Yeah. So linear correlation is the relation. You want to know the configuration? You want to check the
yes,
no.
yes.
Yeah. Okay. Okay. No problem. So just are you able to see the pop-up? There's a pop-up dialog box.
Yes.
Yes. So what I have done here I have included only the numeric values, which consist of integers like age of machine, days since last service, or double T, which are machine temperature, vibration level, radiation leakage, and voltage fluctuation percentage. These are the numeric values. All the pressure bar also I should put. Sorry, pressure bar was also another numeric value. Okay. Pressure underscore bar, pressure in bar. What I have excluded from the correlation matrix is error code, all the string values, error code, usage mode, location type, and also I've excluded MTBF hours, because MTBF hour is the outcome. I don't want to find a correlation between features and outcome, because that's what my regression model is going to give me. My objective is to find out the correlation between two features, so that I know that if the two features are highly correlated, I should do something about it. Clear? Yes or no?
Yeah.
Okay. So I have to run it again. I added one feature. Okay. So now, if I look at the correlation matrix, what is doing is, what is giving is, you have all of these as columns and rows, all the features, age of the machine, days since last service, ambient temperature, machine temperature, vibration, radiation, voltage, and pressure, all of these in rows, and all the similar things are there in the columns. And if you see the diagonal is always 1, because it is a correlation with itself. Age of the machine with age of the machine, days since last repair with days since last service, ambient temperature with ambient. So obviously the diagonal will be 1. And then you have days since last service and age of the machine minus 0.017. So that means there is a weak negative correlation. That means if the age of the machine is high, then days since last service will be less. Older my machine, days since last service will be less. And these two values, again, if you see, is diagonally symmetric. So this matrix is a symmetric matrix diagonally. So 0.017 in first column, second row is the same as second column, first row. Clear? So here you can see certain cases the value is higher, certain cases the value is lower, etc. Is everybody clear? Yes or no?
Yes.
Now, obviously, the question would be that how do I know that two features are highly correlated? Because these are number. How much should I consider as highly correlated so that they should be treated? That means both these features are likely to adversely affect my output model if they are not treated, versus features which are fine. I mean, whatever is the value of the correlation. From this value, I know what is the correlation: high correlation, low correlation, positive correlation, negative correlation, but I do not know exactly whether I should treat them or not. And that is where this is important, where you have a p-value. Remember, p-value is used to accept or reject a null hypothesis. Now, what does this p-value 0.585 mean? What is the null hypothesis? The
Sir,
first column is, yes.
Hello. Sir, this
Yes.
bottom visualization is not coming in my this thing software.
This one is
Yes,
not
this
coming
what
in. What is coming? Maybe a little bit of.
only the above structure, this nodes are coming, but this
But
analysis is not coming.
no. Just see if you can expand this. It should be somewhere here. Okay, and you should be able to expand this. It might be hiding. Have you got it?
No, sir. I tried that earlier. I was resetting my view.
Or otherwise, you just because if you're not seeing it at all, then that is if you're seeing some other value, that's a different. Let me give you the.
No, it's not coming at all, sir.
Okay, one second. I'll just give you the presenter, right? You just. But
I can share my screen, sir, if you want.
Yeah. Do you have the presenter, right?
No, sir.
I don't think. One second. I'll just give you the presenter. Wait. Yes. No, share your screen.
Can you see my screen, sir?
Yes, I can see your screen. Just scroll down. Are you able to expand this? Okay, do one thing. Just right click on this linear correlation. Right click, and view correlation matrix. Go to view. View. Down.
This is coming, sir.
Yeah, okay. Okay, so you are not just let me see, it's giving any other view correlation matrix is not, it should be giving you the detailed values. You go to correlation matrix down below. Yes.
Okay.
I have to check why some of your values are blank. Is it because it is, what is this machine?
Machine number, machine ID.
Machine number issue exclude, na?
Yeah.
Machine ID you must exclude before you do. We said that is a high cardinality value. Right?
Correct.
So machine ID you should exclude and then run the correlation again.
Okay.
Okay.
Fine, sir.
And just okay. So coming back to this, so here you see that the first column and the second column, basically says that what is the two features which are being correlated. Okay, so age of the machine in years and days since first service, the correlation coefficient is minus 0.017 and the p-value is 0.585. Let's ignore the degrees of freedom for the time being. I mean, we don't need to know this. This is statistically a little complicated thing to understand it. We don't require this for this study. Okay. Those who are interested, you can go back to a statistics text. Not required. Okay, for more important for statisticians. So tell me, what does this p-value indicate? 0.585. We normally know that if the p-value is greater than 5%, if p-value is less than 5%, always very confusing. If p-value is less than 5%, you reject the null hypothesis. If p-value is greater than 5%, you accept the null hypothesis. So what is the null hypothesis here? And what is the significance of the p-value here? Anybody? What is the null hypothesis here? No? The null hypothesis is the first column and the second column are not correlated with each other. They are independent and not correlated with each other. Alternative hypothesis is they are correlated with each other. So if the p-value is less than 5%, then you reject the null hypothesis that they are not correlated with each other. So if you go, scroll down, you see basically, is there any case where the p-value is, this is almost close to 5%, but not exactly. Yeah, so here you see 0.001, that means radiation leakage and pressure. Radiation leakage and pressure, these two are correlated with each other. Okay, because the p-value is less than 5%. So ideally, I should not have both these values or both these features in my data set as features to predict the outcome. Now, what should I do with that? That is where again the business input has to come. Will the business say that, look, pressure is more important, leave the pressure and radiation leakage we can do without? Or they may say, we will construct a new metric which will combine the radiation leakage with pressure. Okay. Is it clear, everybody?
But also,
Yes, or no? Yes, please.
When we see the correlation value,
Right.
It is not very close to 1 or -1.
Right.
That means these two features are not correlated
Yeah.
to each other.
Right. But then how much should I go to consider that they are correlated? For example, here, the correlation value also is not very high. It's 0.1. It is not there, it's 0.9. Okay. So it's point.
So here null hypothesis is rejected. That means radiation leakage
and pressure bar are correlated enough to be treated before they are fed into the model. But if I did not observe this p-value, I would not have been able to conclude purely based on the correlation value of 0.106. Yes, of
so
course.
here I can use any one feature and eliminate the other.
That is a decision. So the first, this thing is there is a high correlation. Now, whether I should use any one feature, if one feature, which feature? Okay, which feature according to my engineering sense is more important? This is where the domain knowledge will come in. If you have to drop one of the features, which one is less important? Which one is more important? Or I have to use a combination of both. I have to create a new engineering measure combining both. Okay, so that is where the domain input will come from. Okay.
Yes.
Correct. So as of now, I'm not doing any treatment to outliers, nor I'm doing any treatment to the features that are highly correlated. It's little complicated to do over here. That's why I'm leaving it as of now. Later on, if time permits, we'll do this. Otherwise, we will also be able to do it with this kind of things. It's easier to do it on Python using prompts. So you can just give prompts and say that, okay, remove one of these features, or removal is easy, of course. Removal, I can just filter out one of the features and remove it. But if you have to combine both these features into one principal component analysis, then it becomes difficult. Okay, but as of now, I'm leaving both cases, assuming that it doesn't affect the model to a large extent. And usually when you are building a prototype, building a use case, see, if you look at the cycle, what happens? The business guy identifies a problem, right? You identify a business problem. That this kind of problem probably can have a solution through machine learning. So that's the first step that has to come from you as business guys. Now, once you do that, it's not a good idea to give it directly to the digital team that now build it, because there's a cost to it if it has to be built full-fledged. So usually you build a prototype, a quick prototype using KNIME or similar other tools, where you see it, is it really working? May not be the best model, but is the concept working? Once you are sure that the concept is working, then you fine-tune the model, then you give it to the digital team who is going to work on the details of the model. So that's how the handshaking should happen. So we will not do anything here because we are building a prototype. That's another reason, and we will proceed with the existing data set. What is the next step I should do?
Test and training data?
No. But before that, we have these categorical values. We can't work on that with the categorical values, right? We have categorical values here. Location, usage, error code. We cannot work on that, right? So we have to convert them to numeric, correct? To one hot encoding. Okay, so we have to do this one hot encoding. So one hot encoding is done through a node called one to many. one to many. This will do the one-hot encoding. So I have to select those values where I want to do one to many. Obviously, I don't want to do it for any numeric value. I want to do it only for categorical values. What those error code, usage mode, and location type.
Sir,
These
many
are
to one
the-
or one to many?
Which one did I do? Sorry, one to many, many to one, wrong. One to many. Yeah. Yeah. So one to many, that's why you can see that it is not one, many to one will make the other way around. It will make a numeric value categorical, but here that's why it is showing only the string values. By the way, MTBF hours is coming as string. Let's first see if we have this data set. 1 second. MTBF value should not be string. It will not give us the right answer. Oh, MTBF is string. So there is a problem. If you notice, this data set, the data type is string. So I have to change this data type. Okay. How do I change this data type? Go to transformation. Normally, any of these platforms like KNIME and all, they are good at identifying the data type on its own. But in some cases, as you can see in this particular case, it could not identify it correctly. It actually is a number, MTBF hours, but it's thought it's a string. So I have to convert that to a number. Because if I don't convert that to a number, it will not give me the right, I'll not be able to do regression analysis. Okay.
String means it's an output, sir. What it is?
No. String is not out. A string means it's a text. It's a text field.
Okay.
So it has taken, it has taken this value as a text. It was taking this value as a text. Okay. So now that cannot, once I start building the model, this is the value of y, right? The y value cannot be, it's an equation, right? Y cannot be a text. Okay. Okay. So one to many.
So you can repeat what?
Repeat what I did? Yes, sure.
Yeah.
Just go to this Excel Excel reader. In one of the tab, you see transformation.
Yeah.
In the transformation, you see, not all cases you will get this problem. Some of you, for your case, KNIME could have identified the data correctly. But if the data has been identified as string, then you convert this to D or float. D means double. Float. Okay.
Now, how do we convert this?
Convert it, just go over here, click here, and you see all the different data types. Got it?
No.
So where to
Able to
click?
get it? Sorry?
No, sir. I'm also not getting.
Okay,
From where we need to go to this Excel?
don't
Can you just tell
I think
once
best,
again?
best is to share your screen. Okay. You have you have already the screen share presented. So just share your screen. No, not here. You have to go to the first screen. Okay, just because this is a problem that will happen in the first step itself. Right? Just say, okay, go to the Excel reader. Not here, Excel reader. The first step, Excel reader. First note. Yes. Just go to configure. and go to transformation. Yes, MTPF hours, you see string, change this to, yes, change this to number. No, there should be double. Just go up. There'll be some other. Scroll up. There'll be some other. No, you don't have to put long number. Just scroll up. Double number double. No, it was there. Scroll down. Scroll down a little bit. Number double. Yes. Yeah. Apply this. And need to run it again. Apply. It will reset the node and run it again. No. This one has not been configured yet. Let's see. One too many. What is the problem? Just go to configure. Okay. Now MTBF hours will not be there anymore. Okay, yes, apply. Machine ID remove. Machine ID should have filtered out. Okay. Do one thing. Machine ID you filter out in the beginning itself. Okay. But every time, otherwise you have to filter out machine ID. Just cancel this.
Means into the
just cancel this. I'll tell you. Just cancel this. Because machine ID you should have in the column filter. Go to the column filter. After this, there is a column filter. Okay, yeah. Go to the column filter. Yes. Configure. Here you have not done anything in the column filter. Just remove the yes. So column filter was kind of a dummy node, not doing anything.
Okay, now here it is also done. So I'll just execute.
Yes. Yes. Yeah, now it will happen. Okay. Yeah, but we have to do something here. Okay, so we'll see. Okay. Yeah, I can stop the share.
Okay, sir.
Yeah. Yeah. So in one to many, we have to take these three. Okay. These are the three string values. Okay. And let's see what has happened. See, what it has done is, if you remember the three values, one was the error code. Okay. Now it has made all the error code that was there, none, E01, E02, E03, E04. These are the 5 different error codes. Okay. None means no error, and E01 to E04. It has created 5 different columns and has done a one-hot encoding on that. Okay. Then it was what is done. It has also taken the that was the error code. Then it has taken the usage. Okay. So for the usage, it has again taken the 3 values, 2 values, high, low, and 3 values, high load, normal, idle. For usage, it has taken high load, normal, idle, and done one-hot encode. And for location, it has taken 3 values, urban, rural, semi-urban, and then done one-hot encode. Okay, is this clear? What exactly it has done for one-hot encoding?
No, sir.
Okay, so we said in one-hot encoding, what we are supposed to do? In one-hot encoding, we are supposed to take any of these, okay, categorical values, let's say error code. And we are not going to make it as 0, 1, 2, 3. First of all, the reason why we are doing this is we cannot have any categorical value as a feature, because a regression problem is ultimately we are trying to create a mathematical equation, and a mathematical equation cannot happen on categorical values can only happen on numeric values, y equal to mx plus c. This is the first premise. But then we have some features which are in categorical in nature. For example, location. Now, how do I convert that to number? One option was that we take any of those values and give it a number. But since number is ordinal, there is an order to the number. Moment we do that, some values will get more weightage than others. Whereas there is no reason for giving more weightage. Okay, so that will not work. So what is the solution? The solution is that make all the possible values as separate features. So if location has urban, rural, semi-urban, each of them, urban, rural, semi-urban, will become separate features. And the value should be 1 if for that particular record is urban. The value for all others it will be 0. Rural and semi-urban will be 0. If for another value it is semi-urban, then semi-urban should be 1, all others should be 0. So this method is called one-hot input. So this is exactly what it has done. It has converted urban, rural, semi-urban as 3 different columns and put the value, one of them as 1. There cannot be a situation where there will be 2 1 values. That's why it's called one-hot encoding. Clear?
Understood, sir.
Okay, great. Now, what do you think is the next step? We have been successfully been able to convert the categorical value to numeric value. So what is the next step we should go ahead?
Remove the categorical values.
Yes, very good. Because we already have converted that to numeric value, I should not have any more error code, usage, and location. So then that will be double count, and then if these values remain in the system, I'll again not be able to create a regression line on that. Okay, so I will use a column filter again. And filter out the categorical values. Have to be careful. Error code, yes. Usage mode, yes. And location type, yes. These are the 3 values I have to filter out. Remember, I'm not filtering out their I'm not removing them as features. I have converted them. I've transformed them in a numeric format. Okay. So now I have these values. I have all the numeric values and with MTBF as my target. Okay. So more or less, my data is ready. This entire process, by the way, is called data preparation. In reality, the data preparation probably takes 80 to 90% of the work. Actual work, if you see, is taken by this data preparation, because after that, the models are more or less available. If you look at Azure or AWS, most of these platforms today have already inbuilt models. So you really don't have to create any model automatically. But data preparation is something that really needs to be done. Of course, with generative AI and agentic AI, this data preparation work is also becoming to a large extent automated. But still, there is substantial amount of work to be done. So what is the next step?
Now we have to find the correlation.
No, correlation we have found. Correlation, now you're saying correlation between, yes, of course, the feature and the outcome.
Yeah.
Of course. That's the so, but for that, that's the ultimate objective of our entire exercise, right? Where we have to create the regression line. Okay. So
regression line.
Yeah. To do that, what are the steps? Up to this, it was data preparation.
Now we have to separate testing and training data.
Okay, but before before we do that, another very important step that needs to be done for regression. That is normalization. All the values I have to put in one scale. Otherwise, you can see, because when you are creating an equation, understand this, when you are creating an equation, any equation, you don't consider unit. Correct? Y equal to mx plus c, or m1 x1 plus m2 x2 plus m3 x3 plus c. You do not consider the unit of measure of x1 and x2 and x3. You only consider absolute values. You cannot create an equation with different unit of measure. If the variables are of the same dimension, you can convert everything to one unit of measure. That is fine. Let's say the dimension is length. In one you have kilometers, another you have meter, another you have miles. You can convert everything into meters. That is fine. But if one is kilometer, another is one is length, another is weight, another is something else. Okay, you cannot accommodate that in an equation. The equation ignores any unit. That's the fundamental law of any mathematical equation. But here you have different units. Age of a machine in months and vibration is some other measure. Radiation is some other measure. Ambient temperature is some other measure. The unit. Very, very different units. And because it's very, very different unit, their range is also very different. Ambient temperature of machine temperature 43, 45 like this, but radiation is only 0.061. So if I ignore the unit and put this both radiation and machine temperature both in the same equation, x1 and x2, if machine is x1, machine temperature is x1 and radiation 2, will x2 get any importance or influence on the value of y? Yes or no? Let's say the equation is y equal to m1 x1 plus m2 x2 plus c, where x1 is the machine temperature and x2 is the radiation. Will the radiation get sufficient importance in influencing the value of y? Yes or no? Answer is yes or no? Answer is no, because let's say if the radiation increases from 0.061 to 0.091, okay, 30% increase in radiation. What are you expecting? We're expecting the mean time between failure will come down because there has been significant increase in radiation. But because the value of y is not dependent, this is a very small amount that is causing influencing the value of y. Even if there is a 30% increase in radiation, the value of y will not change significantly. So it will not get reflected as a higher value of y or a lower value of y. Is this clear? Yes or no?
Yes.
Okay. So this is the reason why for any regression problem, you have to always normalize the data. Almost always, unless all the measures are having the same, same dimensionality. It will always normalize it. There are methods of normalization, but we'll just use the simplest one, which is a 0-1 normalization. That means the lowest value in whatever range it may be, it will convert the lowest value to be 0 and the highest value to be 1. Though this is not the best normalization, in a more sophisticated method, you will not use it, because what happens is that if your lowest value is 0, then at the lowest value, that particular parameter has no influence on the output. Okay, because 0 multiplied by, when it gets multiplied by any coefficient, it will become 0. Okay, so that's why it's usually not used. Okay, usually some other range is used, the Z-score and various other things. But for now, we are just going to use the simple normalization. Use a normalizer. And what do you want to normalize on? We want to normalize on everything except mean time between failure. You have to remember this. If you normalize mean time between failure, that will be incorrect. Because that is the outcome that I am trying to predict. If I normalize that, the outcome will become in a range of 0 to 1. Okay. So I can't do that. And so I have not normalized it. So you can see that all the values are now in 0 to 1 range, including the categorical values that has been now converted into different. Fine. Now we are ready. Now we will divide it into training and testing. 70% of the data will give and ask the model to find the nearest possible equation, because we know that the features affect the outcome. We don't know what is the equation. And it's not possible from an engineering or science perspective to find the exact equation. So using machine learning model, we are finding the nearest approximation. Remember the regression, because it may say that initially I mentioned that there is no mathematical formula. Then regression is also a mathematical formula. How is it? So regression is the closest approximation of the unknown mathematical form. We do not know what is the mathematical formula between all of these features and mean time between failure. Okay, the machine learning solution of regression is the closest approximation to that unknown formula. Okay. So we will so we will have regression learner and regression predictor. Okay. Linear regression learner. Oh, sorry. Before that,
partitioning we have to do.
Partition. Yeah. I think I have table partition. You have just partition. The older version had partition. No problem. So we are saying it's the relative distribution, relative partitioning. So we are not saying, okay, a fixed number of records will go to training and a fixed number of records will go to testing. We are saying 70% will go to training and 30% will go to testing. The industry standard normally is 70-30 or 80-20. Okay. And we are saying in this case, the sampling strategy is random. Random means any data that is coming, it can go into training and testing randomly. Okay, till 70% is put in training and 30% is put in testing. Randomly, anything can go. Now, when we go to classification problems, we'll see that you cannot do it randomly. Okay, that we have to use something called stratified sampling. Now, what is this fixed random seed? Fixed random seed means that even if you are taking the 70% randomly, it should not be that the random set of data changes every time. So you are building a pipeline. Okay, I am building a pipeline in my machine. You are building a pipeline in your machine. Now, it should not happen that every time I run this pipeline in my machine, the training data set is different every time, because then I will not be able to get the deterministic result. So for me, at least every time when I run the pipeline in my machine, the training data set should be the same, even though the first time when it was created by random selection of 70% of the data. Okay, so that's what this fixed random seed does. Okay. It fixes the data for the training and testing. Okay. So far, fine, everybody. Great. So
in
do that.
in
Yes, sorry.
partitioning, it is showing as use random seed.
Yes, yes.
That we have to tick.
Yes, it's better to tick. I mean, if you don't tick it, it's going to run. But every time when you run it from your machine, you may get a different result. Okay, because your data set, if for your machine itself, your data set will be different every time you run the pipeline. So we have got the first partition, which is 700, and the second partition, which is 300. Okay, 70-30 has been divided. Now we will use the linear regression learner. Okay. You may ask that why are we always using linear regression? It's not, why are you not using any other form of regression? It's possible that some higher polynomial has a better result. But again, that first of all gets into experimentation. This is what, again, when you actually decide to implement this business case, you may want to check with other regression models as well, not just the linear one. However, most of the cases, in terms of industry data, it is seen that linear regression models are the best. And they're a very interesting study because there is always something called a trade-off between variance and bias. Okay. Variance and bias, the trade-off is very similar to, I think I mentioned this. The analogy is that there can be two types of students. One student who has studied last 10 years question paper. If the question paper comes very similar to last 10 years, this student will do very well. But if there is a slight difference in the question paper, the student will do very badly because the student has not got his or her fundamentals right. The student has only, marked up last 10 years question. On the other hand, there is another student B. So this student is equivalent to having, if this is like a model, the student is like a model. It is going to have very high variance and low bias. High variance because moment the question paper varies a little bit, the student fails. But if the question paper is exactly the same, then the student's bias is very low. The student will get almost 100% marks. On the other hand, there's another student who did not care about going through last few years question papers, but got his fundamentals right. That kind of student will have a low variance, okay, and high bias. So if the question paper is exactly same as last few years question paper, this student will not do that great. The other student who has marked up last 10 years question paper will do great. So bias, that guy has very low bias. So this guy has a high bias. Okay. But if the question pattern changes, this guy has the other student has a very low variance. Okay. And now this student will do much better. So this is where, you should ensure that the model does not overfit. Overfitment means that you have built a model that has a very high variance but low bias, which will work very well if the data set is exactly the same as what it has been trained on. But moment the data set is slightly different, actual data on which it has to predict is slightly different, this will fail miserably. Okay. So that's why you should not have a model that is a very high polynomial model. Because moment you have a very high polynomial model, it will have a very high variance and low bias. It will go through all the individual points, but it will fail if the data on which it is going to predict that is going to that changes that is different from the data on which it got trained. Okay. So what do we want to target now? By it has taken a wrong value, semi-urban. Okay, we don't want to predict that. We want to predict MTBF hours. And all other values are my features. Okay, so it has created the coefficient. So you see coefficient and so coefficient is M1, M2, M3 and intercept. Okay, intercept is a C, right? So our equation is y equal to M1 x1 plus M2 x2 plus Mn xn plus C. C is the intercept and this M1, M2, these are the coefficient. Okay. Now what is this p value greater than t? What does that mean? Anybody? P value less than 5%, we reject the null hypothesis. P value greater than less than 5%, we reject the null hypothesis. So what is the null hypothesis here? So null hypothesis here, if we take any of these, the null hypothesis here is that the mean time between failure so if I put it like this, mean time between failure where the age of the machine is X is equal to mean time between failure and the age of the machine is Y. In other words, the mean time between failure does not depend on age of the machine. That is the null hypothesis. When do I reject the null hypothesis? I reject the null hypothesis when the value of P is less than 5%. That means I'm saying that the mean time between failure depends on the age of the machine. So we can see there are certain values for which the is lower than 5%. Not many, few of them have low. So those are the factors on which actually the mean time between failure depends. Now this is called the explainability of the model. So once I build the model, I should also be able to explain why the model has predicted the way it has predicted. So it helps me to explain that, okay, these are the factors on which the mean time between failure actually depends on. Okay.
Just to
So
clarify, if
yes,
P is less than
5%,
0.05, then you reject the null hypothesis.
Reject the null hypothesis, right?
So
what is the null hypothesis? Yes.
That means null hypothesis is that mean time between failure is dependent on age of the machine.
Not dependent on age of the machine. Null hypothesis is always mu0 equal to mu1. So you can say average mean time between failure or mean time between failure when the age of the machine is X is equal to mean time between failure when the age of the machine is Y. If I take two different ages of the machine, the mean time between failures will be same. Mu0 equal to mu1.
That means mean time between failure does not depend on the age of the machine is the null hypothesis.
Null hypothesis, right. And I'm rejecting the null hypothesis when it's less than 5%. Then I'm saying that it depends on age of the machine. Now, in this case, you can see that mean time between failure does not depend on the age of the machine. Now, this is fictitious data. So obviously, this it does not have any sanctity as such. Okay. But this is really the case when you have your real data and you then see this is where the explainability comes in. Because remember, you had started with an assumption that these are the features on which the mean time between failure depends on. That is what engineering, as an engineer, as a domain expert, you had suggested. But then if you see that many of these features which you had suggested actually does not affect your mean time between failure, then you have to revise, ideally. Okay, so this is called what is a model drift. Model drift means that you revise the features of the model. Maybe there are some other features which have an effect which were not taken account of. Okay, or maybe there is no other features, but then in that case, it is those features which have an effect on the mean time between failure, only those are relevant for building the model. And those are the things that relevant for taking action on. Okay, makes sense, everybody?
So whatever is coming less than 0.5, we have to consider that over here. Means
Yes, ideally, yes. But then,
that
as I said, this is a dummy data, so don't take it as a real serious data that, okay, fine, how come age of the machine is not affecting the mean time between failure? Okay, so, but yes, conceptually, that's the idea. Okay. So let's do the regression predictor. Once you start doing this, you will find it very, very interesting. You don't have to go to always to your digital team. And the only thing is that you have to get your data. Without your data, you will not be able to do the work. Okay. Predicted MTBF. Okay, so this is the predicted MTBF. This is what we have got, and then we know we have to score, find out how good or bad my model is. So it's a numeric scorer. We'll figure out R square. Was predicted. Okay, R square is, you can see, not very good result, 0.371. Okay. That's it. Okay, so yes, of course, not a very good, great model, but you understand the process by which this should be done. Any questions before we close for today? From tomorrow, we are going to start with the classification algorithms, okay, where we try to predict whether a machine will break down or not break down.
Can you explain numeric scorer again, sir?
Yeah, I explain means just the configuration.
Just to show,
yeah, configuration.
Numeric scorer
just,
will give the final values. That
which
means
one?
the mean numeric scorer.
Numeric scorer will give me the measure of the performance of the model. How do I know that the model is performed well or badly or whatever? Okay. So the performance of the model is here is depicted by R square. We have seen R square, the formula for R square, and R square, if it's close to 1, then it is a good model. But again, it should not be very close, not something like 0.9999, but then in that case, it can be an overfitment. But definitely something like anything above 0.9, okay, around 0.9 is good enough. But here you can see it's 0.37, which is a very low R square value. So it's not at all a very good model. But this gives you an idea about how to score the model.
Here in the configuration, what is that you selected? Because it's not visible.
Sorry. In the configuration, there's a reference column. In the reference column, you give the MTBF hours, the actual MTBF hours. Okay. And in the predicted column, you give whatever your predicted MTBF. So the reference column is the original value of MTBF, and the predicted column is what has been predicted by the model.
Okay.
Okay. It is basically comparing your answer with the model answer. That's it. A student has appeared in the examination. The student did not know the answer. Now the student has answered, and now there's a model answer. Somebody is comparing, the TA is comparing the actual answer with the model answer and saying how far the student is accurate. That's it.
Are there significance of other indicators here, the mean and others? Should we
Yes,
ignore
mean, but not so much in terms of accuracy of the model. There's something called adjusted R-square also, but that I'm not getting into more complicated. But yes, it gives you the mean and all those things. Root mean square also is another value. Okay. Yeah, it does have, but R-square is the primary value, okay, which is typically used to check the accuracy of the model.
The final decision or the outcome is that the predicted value is not or the test data is what we are comparing with, right?
Yes, yeah. The final decision is that this model is not good enough to predict the mean time between failure. Okay, so see, this is the reason why this prototyping is very important. So suppose you had a data like this. Okay, you don't give it to the without looking at this. So now you see that the R-square is 0.371. Okay,
If it was above 0.5.
Still it should be at least in the prototype.
0.8.
I should at least go up to 0.7. At least I should go to 0.7. Okay. Because only after I go to 0.7, I can do some more pre-processing, correlation, the things I can take care of and move to probably 0.9. But 0.37, I cannot move to 0.9 anyway. Okay. So I have to go back to the drawing board and say that, look, are these the features on which MTBF depends on? Do I need to collect some more other data? Okay, so that is why this prototyping is so important, because even before I get into the whole process of building a machine learning model, which can be quite expensive, I need to figure out whatever I'm building is a feasible solution.
Or it also can be too much of data is too much of features is there to remove some
Possible,
of the
possible.
not correlated or related features.
Yeah. So there are too many features which are correlated. There may be so many reasons why the model performed poorly. Okay. It may be that there is not enough data itself. 1,000 data points is not good enough. That also can be a reason. Okay. I think I'll see you again tomorrow because we missed one class. I was traveling, so I'll see you again tomorrow on a Sunday. And next week, I think we're meeting in Bangalore.
Yeah.
All of you are coming to Bangalore. Those of you are from Bangalore, yes, but others are also coming to Bangalore.
No, they will join online. Many of them will join online.
Oh, many. Those who are not from Bangalore, they'll join online. No. Okay. That's not too good. I hope to meet all of you there. Then okay. Anyway, chalo then see you. I hope to meet all of you in Bangalore next week. And tomorrow anyway we're meeting. Okay. Okay. Bye. Bye everybody. Bye.
Thank you. Bye.
Bye.
Thank you. Bye.
Hello.
सर अब हो गया खत्म क्लास।
कल अपना क्लास कितने बजे ज्योति?
पता नहीं, अभी मेरे को चेक करना है, चेक करता हूँ।
ओके चलो, थैंक यू।
ओके चलो बाय।